Millions of different chemical compounds are known. All of them are built from simpler substances called elements. Elements combine in countless ways, creating the millions of materials that fill our universe. Elements, substances composed of only one kind of atom, are the fundamental building blocks of matter. They combine to form chemical compounds, just as the letters of the alphabet can be combined to form words. The science of chemistry describes the behavior of substances as they undergo physical and chemical changes. Over 100 elements have been discovered. Each has a unique set of physical properties, like density and melting point, and each behaves a certain way in chemical reactions. But which elements will combine, and how? For centuries, scientists have asked these questions, theorizing and looking for patterns. From a mountain of data, chemists began to seek some unifying principle that would explain why different elements had different properties and different behaviors. The result? The periodic table, an enormously useful tool that scientists could use to discover, learn, and remember properties of the elements. The periodic table relates the elements according to their chemical properties. From an element's position on the table, it is often easy to predict how it will react with other elements. Some elements exist in nature as single atoms, while others exist as two or more atoms bonded together. But most of the matter that makes up the Earth is composed of compounds. Compounds are two or more elements that have been chemically combined, and when that happens, their properties change. Elements and compounds can blend without combining chemically. That's called a mixture. Each part of the matter in a mixture keeps its own identity or properties. It's possible to separate a mixture without changing the chemical properties of the substances. Chemical bonds are the attractive forces which join atoms. To the early chemists, they were the divine forces of nature. Now, we know that chemical bonding involves electrons. The nucleus, buried deep in the center of the atom, takes up only a tiny portion of the atom's total volume. In fact, if the atom was as large as this stadium, the nucleus would be the size of a tiny ball bearing on the 50-yard line. The nucleus doesn't change at all during chemical reactions. Chemical change involves only the electrons. Why do elements in the same family have similar properties? And why do they react to form compounds with other elements? It all has to do with electrons. This model shows electrons arranged in energy levels, or shells, centered around the nucleus. The electrons in this sodium atom are arranged in 3 distinct shells. The number of each row on the periodic table indicates how many shells all the elements in that row or period have. So not only sodium, but every element in the 3rd period has 3 electron shells. The electrons in the outer shell of an atom, the valence shell, have the highest energy. They are called valence electrons. It is these electrons that can be transferred or shared with other atoms in a chemical reaction. Chemists use electron dot structures to show how many valence electrons an atom has. These structures are also called Lewis structures in honor of G.N. Lewis, the American chemist who originally proposed them. You can think of the element symbol as representing the atom's nucleus and all of the inner electrons, with only the valence electrons on the outside. For example, sodium has 1 valence electron. Its symbol is Na, so we would represent it with this dot structure. Each member of a group has the same number of valence electrons, so all of these elements will have similar chemical properties. Lewis dot structures are useful because they can predict how atoms combine to form chemical compounds. some elements react and form bonds with each other. When atoms react, they do so to find stability. Chemical bonds can involve atoms sharing electrons or a complete transfer of electrons. When electrons are transferred, ionic compounds are formed. Ionic bonds occur between metals and nonmetals on the periodic table. Since electrons have a negative charge, when an atom loses valence electrons, it acquires a positive charge, making it a cation. When another atom accepts valence electrons, it acquires a negative charge, making it an anion. These oppositely charged particles are attracted to each other and form an ionic compound. Let's see how sodium atoms react with chlorine atoms to form sodium chloride. Consulting the periodic table, we see that the sodium atom has 1 valence electron and the chlorine atom has 7. The sodium atom easily loses its single valence electron in chemical reactions. The chlorine atom easily picks up valence electrons in chemical reactions. Each chlorine atom with 7 valence electrons can pick up an additional electron to form a negatively charged chloride ion, so it will be stable but charged. When sodium atoms are placed in contact with chlorine atoms, the sodium loses its valence electron and chlorine gains it, forming a positively charged sodium ion and a negatively charged chloride ion. The positive ion is attracted to the negative ion, and an ionic compound, sodium chloride, is formed. We've seen how individual ions combine to form ionic compounds. But how are they arranged? And does knowing this arrangement explain the properties of ionic compounds? Let's consider some of the properties of sodium chloride, which are very different than the properties of either element. First and foremost, the product is much more stable than the reactants. Sodium chloride tends to form crystals that look like little cubes. Sodium chloride is very brittle. You can't pound it into different shapes with a hammer as you can with a metal. Unlike many other substances like ice or wax, sodium chloride only melts at very high temperatures. Let's use our model of sodium chloride as a combination of sodium and chloride ions to explain each of these observations. Like bricks in a wall, ions pack together in a regular way to form a lattice. The oppositely charged ions can come closest to each other when packed tightly into tiny geometric cubes. Here, the positively charged sodium ions pack together with negatively charged chloride ions to form little crystals. We can also use the model to explain why ionic compounds like salt melt only at very high temperatures. Heating a substance causes the particles it is made of to move about more. When enough heat has been added so that the particles can flow past each other, the substance has melted. To melt an ionic compound, the attractions between ions must be overcome. These attractions are very strong, so it takes a lot of energy and a lot of heat to melt the crystal. We've seen how these reactions work on paper. Let's look at one in the lab. The beaker contains bromine, a group 17 halogen. Bromine is found as a red liquid at room temperature. When we add a piece of aluminum, a tremendous amount of energy is released when the aluminum and bromine come together to form aluminum bromide. The properties of the compound are much different than either element on its own. Let's look at other chemical reactions involving bromine that can be predicted using the periodic table. Group 1 elements have 1 valence electron to lose, so they can combine with 1 bromine atom. Group 2 elements have 2 valence electrons to lose, so they combine with 2 bromine atoms. Group 13 elements have 3 valence electrons to lose, so they combine with 3 bromine atoms. We see similar patterns in the formulas for other ionic compounds that involve elements in these groups. Remember, these patterns arise from the charges on ions formed by the elements. Look Looking at the pattern of ion charges on the periodic table, we see that metals, elements with 3 or fewer electrons in their outer shells, lose electrons to form positive ions. Nonmetals gain electrons to form negative ions. But why? When atoms react, they do so to find stability. If we roll the periodic table, it's easier to see how the beginning and end of each row match up. And we notice something unique about group 18, the group that begins with helium, He. The 6 elements in this group do not form ions at all under normal circumstances. Because they don't readily gain or lose electrons, they very rarely interact with other elements to form compounds. For this reason, they're called the noble gases. The noble gases are extremely stable due to the number of valence electrons they have. We find that elements near the noble gases on the periodic table gain or lose electrons until they have the same number of electrons as the nearest noble gas. In other words, until they are stable. Group 1 elements, like this lithium atom, lose their highest energy electron to form ions with a positive 1 charge. On the other hand, elements in group 17, like fluorine, have to gain 1 electron to have the number as the nearest noble gas. Oxygen in group 16 gains 2 electrons to attain the same number of electrons as neon. Nitrogen in group 15 gains 3 electrons to attain the same number of electrons as neon. Elements within the same group have similar chemical properties because of the similarities in their electron configurations. The D-block elements, or transition elements, are metals. It is not so easy to predict the charges on their ions. Compounds of these metals tend to be colorful compared to those of the representative metals, most of which are white. Reddish copper metal can be plated on an electrode placed in the blue copper sulfate solution by passing an electrical current through it. Before 1982, pennies were 95% copper and 5% zinc. After 1982, pennies were mostly zinc with a thin copper-plated coating. We can see the difference by putting old and new pennies in nitric acid. Once the copper coating wears off the newer penny, the zinc begins to react with and produce very rapidly evolving brown NO2 gas. In the other beaker, the copper penny continues to dissolve as the solution turns a deeper and deeper blue. Some transition metals form useful alloys, mixtures containing more than 1 element. For example, pure 100% gold is 24 karat. Most jewelry is made from an alloy of gold with copper or some other element to give it strength, since pure gold would be too soft. Nickel and titanium form an alloy called memory metal with a curious property. It can remember its shape, and when the temperature changes, will spring right back to its original form. Not all compounds can be explained in terms of electron loss and gain between atoms. There is another way for atoms to chemically bond using their valence electrons. When atoms share a pair of electrons, they are linked by a covalent bond. Covalent bonds are sometimes represented as a line rather than a pair of dots. Molecules are groups of atoms that are held together by covalent bonds. A molecule can have as few as 2 atoms, like hydrogen gas, or as many as millions, like DNA or polymers in plastics. Covalent bonds typically are only formed between pairs of nonmetal atoms. The simplest covalent bond is the single bond. A single bond exists between 2 atoms that share 1 pair of electrons. There are also double and triple covalent bonds. Each nitrogen atom has 5 valence electrons. That means that nitrogen and all group 15 elements can either accept 3 electrons to become a triple negative ion or join in a covalent bond with 3 other items. nitrogen gas, N2, contains a triple bond. By sharing 3 electrons with another nitrogen atom, it can attain the 8 valence electrons it needs to be like the nearest noble gas, neon. Nitrogen makes up about 80% of air. Liquid nitrogen is used to cool systems in modern laboratories. Its temperature is 77 degrees Kelvin. Flowers disintegrate, and a magnet floats on top of a superconducting pellet cooled in liquid nitrogen. White phosphorus is a waxy substance that burns spontaneously in air and must be stored covered with water. Red phosphorus is much less dangerous than the white variety. The reactive white phosphorus consists of P4 molecules, while the red variety is a giant network of P atoms. What is commonly referred to as arsenic in murder mysteries is usually the tasteless white compound arsenic trioxide, not the brittle dark gray crystals of the metalloid element arsenic. Let's review some of the patterns we can see using the periodic table. In general, we find that metals, elements on the left side of the periodic table like sodium, calcium, iron, and gold, tend to lose electrons in reactions. Most elements are classified as metals. Nonmetals, the elements on the right side of the table like sulfur, tend to gain electrons. And metalloids are elements like silicon and arsenic that have properties of both metals and nonmetals. All of the nonmetals, except for the noble gases, exist as covalently bound molecules. Elements close to the border between metals and nonmetals often form vast networks of covalent bonds. For example, carbon atoms link together in many different ways. Carbon atoms can link to form a soft substance known as graphite. Carbon atoms can also link to form diamond. Every carbon in diamond is covalently bound to 4 other carbons. Actually, we can consider a diamond as a single gigantic molecule. Covalent bonds are exceptionally strong, and as a result, diamond is an exceptionally strong material. In fact, it is one of the hardest substances known. Carbon compounds form the basis of all life on Earth and provide some of the energy produced by the Sun and other stars. We've seen 2 descriptions of bonding in molecules: transfer of electrons in ionic compounds and sharing of electrons in covalent compounds. Many compounds contain bonds that lie between these 2 descriptions. Electrons are shared in these molecules, but they are shared unequally. Let's look at the formation of hydrogen chloride, HCl, from hydrogen atoms and chlorine atoms. Hydrogen has a single valence electron, and as we've seen, chlorine has 7. By sharing a pair of electrons, each can become stable, attaining the configuration of the nearest noble gas. Chlorine has more protons, so it has a much larger positive charge on its nucleus than hydrogen does. Although its inner electrons partially neutralize this charge, it still has a greater attraction for the shared electrons than hydrogen does. As a result, the electrons in the bonding pair aren't shared equally. The chlorine end of the molecule is richer in electrons, so it has a partial negative charge, and the hydrogen end is electron deficient and partially positive. We say that the bond is polar, kind of like a magnet, with a positive end and a negative end. Let's compare 2 compounds, water and acetylene. They seem pretty similar on the atomic level, but their properties are very different. Why? An acetylene molecule is linear and nonpolar, while water is bent and polar. In preparing solutions and mixtures, we often want to be able to predict the polarity of a bond or a molecule in the mixture. Why? Because like dissolves like, and polar substances and nonpolar substances tend not to mix together very well. For example, water molecules are very polar, but molecules of oil or grease tend to be nonpolar. So oil and water don't mix well. Is there any way we can predict how polar a bond or molecule is going to be? We know that chlorine has a greater attraction for bonding electrons in the HCl molecule than hydrogen does. If we could rate various elements on the periodic table according to their greediness for bonding electrons, we could easily predict the polarity of any bond between them. The first scale for electron attraction was devised by the American chemist Linus Pauling. He called it the electronegativity scale. Fluorine is the most electronegative element. Pauling assigned it an electronegativity of 4.0. Oxygen is second at 3.5. All of the nonmetals except for the noble gases have high electronegativities. That makes sense since we've seen that these elements tend to grab electrons from other atoms when they form ionic compounds. The metals have low electronegativities. We've seen that they surrender their electrons when they form ionic compounds. We can see some regular trends in electronegativity on the table. Electronegativity tends to go up as we move towards fluorine on the table. Electronegativity generally rises going left to right across a row, and it drops going down columns. Notice that some of the noble gas elements on our table do not even have electronegativities assigned. With their full valence shells, they aren't greedy for any more electrons. Using Pauling's electronegativity scale, we can see how atoms will pair up. We can tell whether a bond is ionic or covalent by looking at the difference in electronegativities for the bonded atoms. A large difference in electronegativity means that electrons tend to be transferred between the atoms rather than shared. For example, the metal sodium has an electronegativity of around 0.9, but greedy chlorine has an electronegativity of over 3.0, so we describe the bonding in NaCl as ionic. If one atom has a somewhat higher electronegativity than the other, this will cause the electrons to be shared unevenly. This bond between hydrogen and chlorine is an example. It's described as polar covalent. Two atoms with the same electronegativity, either both high or both low, will form nonpolar covalent bonds. Some bonds are stronger than others. Weaker bonds are more susceptible to breaking in chemical change. By understanding the relative strengths of bonds in a molecule, we can gain some insight into what's really happening in reactions that involve that molecule. We can measure the strength of a bond by measuring the amount of energy it takes to break it. This energy is called the dissociation energy. The greater the dissociation energy, the stronger the bond. Let's compare the dissociation energies for the bonds in N2, O2, and F2. The bond between nitrogens in N2 is the strongest, and the bond between fluorine atoms in F2 is the weakest. But why? Let's compare the dot structures of the three molecules. We can immediately see that N2 has a triple bond, O2 has a double bond, and F2 has a single bond. This explains much of the difference between the strengths of these bonds. We've seen how the behavior of the elements and the compounds they form is related to their location on the periodic table. And we've used the table to predict the character and strength of chemical bonds, which are electronic links between atoms in compounds. The periodic table is a remarkable tool for predicting the properties of elements and the compounds that form from them. By using the table to study the formation of bonds and trends in properties in a series of compounds, we've gained some insight into the way chemists search for compounds that can be used for particular applications. The periodic table is a valuable tool in the search for new polymers, new medicines, and new agricultural chemicals.